Hello, everyone. What I want to do now is talk very briefly about completeness for normed vector spaces. First, I want to make a fairly obvious observation that I'm sure all of you are aware of. In particular, let's say X be a normed vector space. So unless otherwise stated, big X will always be a normed vector space. Then you can turn X in a fairly obvious way into a metric space in basically the obvious way, where D, the metric, is given by, for X and Y in big X, just a norm of X minus Y. So the axioms of a norm immediately tell you that this, in fact, is a metric on X. So from that perspective, we can talk about convergence, completeness, et cetera, in my normed vector space. Okay. Okay, but still, I think it's useful just to remind you of some of the basic definitions without recourse to just saying, well, it's just the usual metric space definitions. Okay, so let me talk about completeness. So remember, Xn, a sequence of elements in my normed vector space, is Cauchy. Well, it's Cauchy if it's Cauchy in the sense of turning X into a metric space, which translates to, for any epsilon bigger than 0, there exists n depending on epsilon, that's a natural number, where m n bigger than n implies xn minus xm in norm is less than epsilon. Right, so we say big X, a normed vector space, is a Banach space named after the famous mathematician Stefan Banach. And in our book, before I write anything more, in our book, there's a really nice page or two little biography of Banach, and particularly his unfortunate experiences in World War II, though he did survive, thankfully, luckily. He did survive World War II. A lot of Polish intellectuals, sadly, did not survive World War II. But anyway, definitely take a look at that. It's very interesting how he ended up surviving World War II. So yeah, X is a Banach space if, well, as a metric space, X is complete. Okay, so in other words, Cauchy sequences converge. Okay, so in other words, well, what does this mean? There exists X in my Banach space where xn converges to X, which by definition is saying that, well, again, just standard convergence in a metric space definition. Xn minus X converges to 0 in norm. Right? Yeah, so Xn converges to x, by definition means that this limit here that I'm going to put in red is 0, right? Okay, so some examples of Banach spaces are as follows. So here, P is between 1 and infinity. Well, certainly the complex numbers and if you've never seen this, a proof of this before, try and prove it yourself. It's very easy. Actually, we'll prove later on that any norm on a finite dimensional vector space gives you a Banach space. So any finite dimensional norm vector space is a Banach space. So continuous functions on 0 to 1 or A to B under the norm I talked about last time, the sup norm, really max norm, whatever. Yeah, this is big C for continuous functions on 0 to 1. That's a Banach space. Probably proved that in 511. So as a nice example of proving something that you might not have seen is a Banach space, I'm going to just from scratch prove that little LP is a Banach space. We all know that LP, the very least over the real line, really same proof works over any general measure space, but LP with the LP norm is a Banach space. So let's prove that this is a Banach space. So here I'm not going to prove this for P equals infinity. Maybe I'll leave it for homework. We'll see. I have to very judiciously pick my homework in this course because there's just so many possible homework assignments I could give you, and I don't want to do that. I had some complaints last time about homework, but anyway. Yeah, I mean, anyway. Right, so let's prove this. Okay, so let's say I have a sequence of elements in little LP. So each xn is an element in LP. So of course that means each xn itself is a sequence of complex numbers. And among this sequence that I'm writing, I'll use subscripts for the first, second, third, et cetera, element of that sequence. Superscripts are going to denote the kth element in this sequence of elements that are in little LP. Okay? Notation is always cumbersome when you deal with sequences of elements that are in itself a sequence space, but anyway. Okay, so yeah, so let's say this is Cauchy. So for any epsilon bigger than 0, there exists n natural number n where, well, I'll just rewrite the definition. I think it's quite useful. So x m minus xn, LP norm is less than epsilon. Well, what is that? Because we're going to have to work with it. Let me explicitly write it. So as j equals 1 to infinity, xm j minus x nj p 1 over p. This is less than epsilon. So you'll note that if J0 is a fixed natural number, then let's make a fairly trivial observation here. Well, what I could do is I could do something kind of silly here, which maybe is not so silly. I can just raise it to the power p and then raise it to the power 1 over p. Again, p is not infinity here. So. Right, so what's the purpose here? Well, certainly inside these brackets, this one single term is less than or equal to this entire sum, because this entire sum is most certainly going to contain this one single term. And this whole entire sum that I'm writing, well, I mean, this is a little LP norm of xm minus xn, that's less than epsilon, as long as m and n are bigger than big N. Well, what does that mean? That means, so again, maybe make this more clear. Let me get rid of p's here. So that means this is a Cauchy sequence, again, for J0 fixed. Sorry. Right. Right, so maybe I should use K or something, but whatever. I don't think it really matters, but if there's any confusion, yeah, I'll write another letter. But anyway, this says that because obviously each one of these is a complex number, we have a Cauchy sequence of complex numbers for each fixed J0, and hence it converges. So let's define xj0 to be this limit here, which for each so here I do want to use, actually I want to use m here. Right. Right. Yeah, so Cauchy sequences of complex numbers converge. So there's no claim of uniformity in M whatsoever, just for fixed J0, this limit exists as a complex number. So this is kind of our obvious candidate for X. In particular, let's say X is X1, X2, et cetera, et cetera. All right. So I claim that in the limit, this is going to be 0, okay? And well, by the triangle inequality, that's also going to imply, in particular, that X is in little LP. So check that if you're in doubt whatsoever. Okay, so how do I prove that? So let's fix a natural number, K. So, well, I mean, if you want, you really could just use Fatou's lemma for, uh, you know, infinite sums, but you don't have to do anything, anything like that. We don't really need Fatou's lemma to do this. Right. So, let me just rewrite the Cauchy. Let me just rewrite what I have here. Right. Oops, went the wrong way. Sorry about that. Right. So epsilon is less than this sum here. So actually, so if m is bigger than big N, right. So, oops, sorry about that. So we can let n go to infinity. And use the Cauchy, property. Maybe I'll go back and explain this more in a second if it's unclear. So it should be pretty clear that this is okay. So in particular, right, here, as long as n and m are bigger than n, this is true. This sum here is less than epsilon. Well, if n goes to infinity and m is bigger than n, certainly n and m are bigger than n, so this is certainly true, taking a limit, so less than or equal to. Well, we don't know if the limit really exists, so we really do have to do lim sups, which always exist. And in particular, the lim sup is less than or equal to epsilon. Okay. Well, what we can do is, this is certainly bigger or equal to this lim sup here. Just sum up over the first k terms. So the point here is I'm avoiding any kind of, murky interchange of sums and limits, infinite sums and limits. Okay. Well, so now for each j equals 1 to k, this is just a finite sum. So I can certainly move in this lim sup. Certainly I can move it into the 1 over p, and I can certainly move it inside here. Maybe just to make absolutely clear, this is going to be equal to, again, it's a finite sum, there's no issue here. So lim sup, n goes to infinity. Xj, what did I put first? N. Well, there's no ambiguity about limits here. For each j, xn converges to xj. That's the definition of xj. Okay, so this is going to be equal to j equals 1 to k. And again, nothing wishy-washy here. Everything, everything is very rigorous. Okay, so for any natural number k, this sum, j equals 1 to k, of this right here is less than or equal to epsilon as long as this is true. As long as what I'm going to put in blue is true, then epsilon is bigger or equal to this sum here. Okay, so there's no harm in letting k go to infinity and using the definition of an infinite sum of at least non-negative numbers. So that implies that j equals 1 to infinity by letting k go to infinity. Well, this here is less than or equal to epsilon if m is bigger than n. And of course, that's the little LP norm of x minus xm. And hence we have convergence. Right, so nice little proof and a nice little trick to keep into the back of your mind. If it's ever murky to kind of interchange limits and sums, just think about a finite sum where that's trivial and then let the number of terms go to infinity. If you can get an estimate independent of the number of terms you're dealing with. Okay, so next what I want to do is talk about the Bergman space very briefly. You probably did this in Kehei's course. Maybe my proof is going to be a little different. Okay, so yeah, so let me go over this example here. Let's say, so D is a unit disk, and we all probably know it's just all complex numbers where modulus W is less than or equal to 1. Let's say this is going to be, well, the vector space of all holomorphic functions on the unit disk, where you integrate f over the unit disk. It's finite. Okay. Yeah, and here dA is just ordinary area measure. And really this is an ordinary two-dimensional Riemann integral because f is, well, modulus f to the p is continuous because f is holomorphic. It's really an improper integral because f is most certainly not necessarily defined on the boundary. Boundary behavior of functions in AP is a very, very challenging question. I'm sure there's a lot of things to be proved about that. It's really just something that's not easy to handle. But anyway, so yeah, this is just all holomorphic functions on the disk where this integral is finite, and you give, well, the obvious norm. And actually, it's kind of a pain to write the disk all the time, so just writing AP. Well, it's just the natural LP norm corresponding to this definition. And I don't know why it's called AP. I don't know where big A comes from. Maybe A for area. I don't know. But anyway. So I want to prove that AP is complete, at least for P between 1 and infinity. The correct kind of analog when P equals infinity is not very clear. I believe maybe you talked about it in Kehei's course. I believe it's a little block space. Maybe I'll talk about that as the course goes by. But in a sense that the dual of A1 is a little block space, if I remember correctly. Maybe even prove that, because it's a nice use of Banach theorem. Okay, so actually first, I need a little lemma. So you probably proved something more difficult in Kehei's course using the hyperbolic geometry of the unit disk. I don't need anything really fancy here, so the first thing we need to do is get a pointwise estimate for f on the unit disk. So in particular, we're going to prove that if W is in a unit disk and F is an AP, then we have the following estimate. So you can do a little better. You can actually get the squared 1 minus modulus W squared. But yeah, that's what you probably did in Kehei's course. That's quite a bit harder using, the pseudo-hyperbolic metric and Möbius transformations. Yeah, anyway. And again, this is for W and unit disk. All right, so this is really just easy consequence of the mean value theorem and Holder's inequality. All right, so if we have an R between 0 and 1 minus modulus W, then I claim, I claim that, and I'll explain why I'm doing this in a second. Well, I want to apply the area mean value theorem to this disk. So let's assume Z is in this disk here. So yeah. So if Z is in this closed disk here, this is fairly trivial. Then just add and subtract W. Use the triangle inequality. Z minus W in modulus of Z minus W is less than or equal to R. And R is strictly less than 1 minus modulus W. Okay. So Z is in the unit disk. Okay. Okay, so in other words, what does that tell me? Well, in particular, F is holomorphic on this. Well, F is holomorphic on the unit disk, so certainly F is holomorphic in a neighborhood containing this closed disk, and hence I can use the area mean value theorem from 513a. Okay, we need the closure of this disk to be in the unit disk for us to be able to use the area mean value theorem. So it's 1 over pi r squared. So just integrate this over this disk, okay? And you'll notice you can't just let R be 1 minus modulus W, because in that case, if R is 1 minus modulus W, well, then this is equal, so all we have is modulus Z is less than or equal to 1, and that you can't have that. In order to use the mean value theorem, the area mean value theorem here, you absolutely have to have F is holomorphic in an open set containing your closed disk. But that's all right. We're just going to let R go to 1 minus modulus W in a moment. But for now, it's strictly less than 1 minus modulus W. All right, so I'm going to take this area mean value theorem, and in particular, take absolute value or modulus of both sides, and that's going to make this an inequality here. Now I'm going to use Holder's inequality. Really, if you think about it, you have a perfectly fine probability measure here. And you can just use Holder's inequality with respect to that probability measure, or just use the traditional Holder's inequality. That's fine. If p equals 1, you don't do anything. So let's assume p is strictly between 1 and infinity. So this is going to be f of z in modulus p 1 over p. And just integrate 1. No harm in ever using Holder's inequality like this. Okay, and you should check, well, of course, this blue. This is just the area, 1 over pi r squared. So you have 1 over pi r squared times 1 over pi r squared to the 1 over p prime. And, well, that, oh, sorry, that doesn't make sense. It's not 1 over pi r squared, it's pi r squared. Whole thing is pi r squared. Okay, so let me, so this is going to be pi r squared to the 1 over p prime minus 1 times this here which lo and behold just gives me 1 over pi r squared to the 1 over, pi r squared to the minus 1 over p. So this is going to be equal to 1 over pi r squared. I'm bringing that inside the 1 over p. Yeah, and that's because, again, let's go back here, 1 over p prime minus 1 is minus 1 over p. 1 over p prime minus 1 is minus 1 over p, right? So this, we get pi r squared to the minus 1 over p, bring inside to 1 over p. And finally, well, yeah, finally, so finally what we do is we let R approach 1 minus modulus W. That's fine. We have an estimate here. So actually, before I do that, let me do one more thing. So this is going to be less than or equal to 1 over pi r squared 1 over p. Well, certainly I can just throw out this ball and replace this with the Bergman space norm. because BWR, the closure, is contained in the unit disk. So. Yeah, so finally, just simply let R approach 1 minus W squared from the left. Okay. So in particular, if that's not clear, I haven't used green yet. So what have I actually proved? Going back, I proved that for any, right. So for any R between 0 and 1 minus modulus W, f of W in modulus is less than or equal to 1 over pi r squared to the 1 over p times the norm of f. No harm whatsoever in letting r approach 1 minus modulus W. So you do that, you get exactly what you want, which is this green inequality where we have 1 minus modulus W. Okay, so anyway, enough of that. Let's prove completeness. Okay, so the easiest thing to do is, well, utilize the fact that LP over the unit disk is complete. Okay, so let's say we have a Cauchy sequence. Okay. Now, AP is certainly a subset of LP. And just this once, I'll write over the unit disk. And they have the same norm. I mean, this, sorry about that. This is just the LP norm over the unit disk. So, right, with, so, same norm. Well, what does that tell me? It tells us that we have a Cauchy sequence in LP, and we know that converges to something. So let's say Fn converges to F in LP of the disk. Right. So here, this is an LP of the disk. Okay. So we need to prove, so we have convergence in the AP norm, basically. The AP norm is the LP norm. Only problem is we don't know that F is homomorphic on a unit disk. So yeah, I like using ETS. So it's enough to show that F is holomorphic, and this is fairly straightforward using my lemma. So that's to show that F is holomorphic on the unit disk. So in other words, what are we really proving? And this is something that's very useful to remember. We have a Banach space LP. We have a vector subspace AP. It's certainly a vector subspace, a normed vector subspace. So to prove that AP is a Banach space, all we really need to do is show that it's closed, meaning that if I have an F that's a limit point of my vector subspace, then that F is in my vector subspace to begin with, okay? Because Right, because then if y in general, well, if you have Fn and AP, it's Cauchy, then that converges to something in your bigger vector space in general. And if we're dealing with our original space is closed, then by definition of closed, that'll mean F is in my original space, i.e. in this case, F is holomorphic. F holomorphic and F and LP means F is an AP. We already have the LP, we just need to prove it's holomorphic. Okay. So maybe what I just said I'll write down as its own proposition when I'm finished with this. Okay, so all we're going to do is use Morera's theorem. All right, so we have to start off with a compact K. Okay, so we can certainly pick a little ck between 0 and 1, where W and K implies that modulus W is less than ck. I mean, you can always do that if K is compact. So that means 1 minus modulus W, if W is in K, is greater than 1 minus ck, which of course is in 0, 1. So in particular, we have a lower bound for 1 minus modulus W as long as W is in K, and that lower bound is just dependent on K. All right, so let's apply my lemma to Fn minus Fm. Okay, again, I want to use Morera's theorem. So I need to show that my sequence here, Fn, is uniformly Cauchy over each compact subset. Okay, so Fn W minus F M of W. Okay, so again, let's use this lemma here, where instead of F, we have Fn minus Fm. Okay, so this is going to be less than or equal to the max of W over K, 1 over pi, 1 minus modulus W squared to the 1 over P times the norm of Fn minus Fm. But we know that 1 minus modulus W is less than or equal to 1 minus ck. Obviously, 1 minus modulus W is between 0 and 1, but in particular, it's less than or equal to 1 minus ck. So this is going to be less than or equal to max W is in K, 1 over pi 1 minus ck. So this is between 0 and 1. Remember, ck is between 0 and 1. Well, the thing is here, there is no W, so it's almost silly to write max here. This is completely independent of W and K. It's certainly going to depend on K because ck depends on K. As K takes up more and more and more of the unit disk, ck might be forced to 1, in which case this would blow up, but that's okay. This is just a constant depending on K. Okay, so that implies, well, Fn, the sequence, of course, of holomorphic functions on a disk, is uniformly Cauchy on each compact and that's going to imply, I got to be a little careful, that implies that Fn converges to some holomorphic function. We don't know what it is exactly, but just some holomorphic function uniformly on all compact subsets of the unit disk, but in particular pointwise. For this, yeah, as I said, for this F tilde here, that's holomorphic. Okay? That's basically what Morera's theorem says. If you have uniformly Cauchy on each compact subset of any open set, then you have convergence of Fn to a holomorphic function uniformly on each compact subset, in particular pointwise convergent. In particular, you have pointwise convergence. Okay, so finally, well, for almost every z in the disk, well, we have Fn converges to F in LP, so we know that we have a pointwise almost everywhere convergent subsequence that converges to F of z. But for each, maybe I should say, not that it matters, but just because I wrote it like this here. Okay, so what does this says? Well, this says certainly we know that for every z, Fnk converges to F tilde of z. So in particular, for almost every z, F tilde equals F. So F is holomorphic, or maybe more precisely, you can pick a representative of a class generated by F that's holomorphic. That's exactly what this says. I mean, F tilde is holomorphic, and F equals F tilde almost everywhere. So anyway, so that proves it. So as I said, I basically stated the proof, but if there's any confusion on my proof, definitely do this yourself. I think this may be too easy for a homework to collect. But so we really proved the following proposition, which is quite useful. I mean, if you forget, it's not a big deal. It's just you're probably going to just reprove it if you ever prove, if you ever end up using it, basically. So let's say X is a Banach space. If Y is a subspace, a normed vector subspace, then in fact Y is a Banach space, so it's complete. Well, if and only if, because it lives inside of a nice Banach space, if and only if Y is closed. Okay, so that finishes this lecture up. Next lecture will be on the completion of a non-complete normed vector space. And this is not, it's not something that's just you do just to be abstract and silly. I'll introduce Sobolev spaces through this completion process. And because it's probably going to be new for everyone, maybe I'll actually go over weak derivatives, which you definitely have to master if you're going to work particularly with Marius or Ivana. I do some PDEs myself. I particularly do elliptic PDEs. So I definitely use Sobolev spaces a lot and weak derivatives a lot. Anyway, yeah, so I'll go over completions, go over some natural norm vector spaces that are not complete, but you wish they were complete, so you do the next best thing, you complete them. So anyway, yeah, I'm sure all of you have seen completion before, but I'm guessing maybe some of you have not seen Sobolev spaces before. So, all right, so long, take care. Yeah, until next time.